In this lecture, I want to introduce a brand new topic, energy. To introduce this topic, I want to start with a question you already know how to answer. How fast will this box be going at the bottom of the ramp if the box is released from rest and there is no friction between the box and the ramp surface? We are given tilted axes shown here at the bottom of the ramp because the box is only moving in one dimension. We are given the distance the box travels. We are not given time. So to find V final, I would start with the time-independent equation of kinematics. And keeping in mind what we learned about inclined surfaces, our acceleration down the ramp would be g sine theta. Substituting in our known values, we determine that the box is going 7.7 meters per second when it gets to the bottom of the ramp. Down here. What if you were asked how fast the box is going when it reaches the bottom, but instead of sliding down the 5-meter length of the ramp, it just falls off the back? I could use that same kinematics equation, and now the acceleration is 9.8 meters per second downward, and the displacement is 3 meters, also downward, and I determined that V final would be 7.7 meters per second at the bottom of the ramp. Personally, I think it's interesting that these two blocks took two different paths, and we calculate that they are going the same speed when they get to the bottom. I want to be clear, the one sliding down the incline will take more time to get to that speed. Their accelerations are not the same. But they do get to that same speed by the time they're at the bottom of the ramp. So this hints at the idea that there is something that occurred to the box that has to do with how high it started, more than it has to do with the actual length of the path that was taken. And that leads to our idea of energy. I want to take a moment to note that when we talk about energy in physics and in chemistry and in engineering, biology, ecology, we're talking about the same thing, but we don't always stop and define what energy is very clearly. And I think that's actually okay, because how we use the concept of energy is probably of a lot more utility than stopping and giving a specific definition in most cases. If we were to define energy, we would say it is the ability to do work or the ability to enact change on a system. In fact, the word energy comes from the term for stored work, which we will talk about soon. In the meantime, I'd like to give you some key points about energy. For example, you may already know that energy cannot be created or destroyed. It's important to also know that energy can be transferred from one object to another. Energy sometimes may seem to disappear from a problem until you recognize that it can be stored due to an object's physical location in a field or due to an object's elasticity. A field is a description of how objects can interact with one another at a distance without touching one another. For example, gravity pulls down on you whether you are touching the planet Earth or not. We refer to that fact as Earth's gravitational field. Energy can be stored in that field in ways that we will be talking about in this lesson and the next few lessons. One of the best parts about studying energy from the perspective of a physics student is that energy is not a vector. So when you are doing problems and you think maybe you could solve it with kinematics and forces, like the boxes on the ramp, kinematics and forces are vectors. Well, maybe you could solve that same problem with energy, and it's probably a good idea to try to do that because it simplifies a lot of the vector addition we've been dealing with up till now, depending on what was given in a particular problem. The idea of energy in a lot of ways can be traced back to thermodynamics. For example, this is a picture of a temperature probe in an ice bath, ice and water at 0 degrees Celsius together. If you were to place a small, hot, 100 degrees Celsius piece of metal into this ice bath, you would expect to see the temperature of that metal object go down and the temperature of the water go up, and the temperatures would meet somewhere in between. Exactly what temperature they would meet at would depend on what metal you have and how massive it is, but it would seem that something is transferred from the metal to the water. The metal loses temperature and the water gains temperature. What is it that's transferred? And why does that happen to all objects in an isolated system over time? In the 1700s, scientists were trying to answer that question, and they had the idea that maybe heat is some kind of fluid that we can't see directly, but we can tell it's flowing from one object to another if there's a temperature difference. Today, we no longer think of heat as a physical fluid, but we still talk about it like that in a lot of ways. We talk about heat transfer and heat flowing. We often depict it as if it's some substance flowing from one place to another. There's a lot of validity in thinking of heat that way. By the 1800s, engineers were using heat transfer extensively in steam engines and to power locomotives, ships, mining equipment, or to generate electricity. The idea that something is stored, for example, in coal, and it can be transferred out to be used by machinery to produce something useful work for scientists and engineers, helped those scientists and engineers to settle on the concept of energy as we now know it. It's exactly how we still describe things today, like how a nuclear power plant generates electricity for us to use in our houses to make heat, light, etc. I want to emphasize the idea that energy is useful only because we know energy is conserved. That is, if we can determine the amount of energy in a system at one time, we know that we will have that same amount at a later time, although it may have changed what format it is or which specific object in the system has the energy. I'm linking this slide in the notes to a video explaining how Richard Feynman thought about the concept of energy, why he thought it was very useful. I'm recommending that you check out that video, again, linked in your notes. I'm also sharing these terms in your notes. You'll want to be familiar with these. As it says here, if a system is described as isolated, that means the total mass and total energy in the system are constant values. So you would assume that the system has not had contact with the rest of the universe during the course of that problem. There's also the term closed. If a system is described as closed, it means the total mass of the system is constant, but energy can be changed through interaction with something from outside of the system. We will be talking about conservative forces, which can change an object's energy between kinetic and potential, the type of energy that an object has. But as it says here, conservative forces only act within a system. And we will also talk about non-conservative forces. For example, a non-conservative force would be something like a hand pushing on the object that we're studying, or the force generated by an engine that converts chemical energy to mechanical energy or something like that. Another common non-conservative force that we will talk about is friction, which changes kinetic energy from kinetic to thermal, and energy cannot easily be transformed back from thermal energy to kinetic energy for an object. So again, these terms you'll want to be familiar with. I said a non-conservative force can add or remove energy from a system. For example, a hand reaches into the problem and gives a lab cart a push. The big picture here is that there are only 3 ways you can change the energy of a system. And in this course, we really only talk about one of those ways. That's the W here. A force acting on a system can change the energy of the system by what we call working on it. The Q and the R are also ways to change the energy of the system. We don't really get a chance to talk about those in this particular course, but again, this slide is about the big picture, so I want to make sure I included them. The types of energy we're going to focus on are the energy of an object due to the object being in motion. We call that kinetic energy. There's an equation for it given here. And the energy an object has due to its temperature, we call that thermal energy. Note, I'm not giving an equation for energy due to temperature. And this mostly comes up for us in the idea that friction converts an object's kinetic energy to a different kind of energy, and the objects involved both have an increase in temperature when there is friction. The text that's highlighted in blue here, or rather is in blue font, these are different types of potential energy. We have potential energy due to a spring or other elastic material. We have potential energy due to gravity that we will be talking about in this course. There are other types of potential energy that you would be talking about if you went on to take other physics courses. So in this video, I just want to introduce those terms, and in the next video, we will talk about how to use those equations, and I will introduce a few other equations that are related to the ones that I just showed you.